Hey guys, we're back here with the second part of 9.1. Again, we're looking at the difference of two proportions, and now we're going to take a look at hypothesis tests for two proportions. All right, so here's the plan for the hypothesis test. So again, there's lots of stuff we have to do. It's basically like doing everything twice. So we have to state what both p's stand for, p1 and p2, or whatever letter we use for the subscripts or numbers or whatever. All right, and again, don't forget to write that they are the true proportion of something or other. For the null hypothesis, it's either that the difference equals 0 or that p1 equals p2. I will probably usually go with p1 equals p2, but really what's happening is p1 minus p2 equals 0 is why we get the name for the test like p1 minus p2. All right, the alternative hypothesis will be that either they don't equal 0, one's greater than 0, or it's less than 0, or we can be like p1 doesn't equal p2, or p1 is greater than p2, or p1 is less than p2. Any of those are fine. I usually go with these ones down here. So mine will probably look like that. And then list all of our known statistics and alpha. So we're back to having an alpha value since we're doing a hypothesis test. Remember, alpha looks like that. Right? And if we don't have an alpha, we use 0.05. All right, then we state the name of our test. Again, we're looking with two samples. All right, ZapTax reminds us that we are working with p's, so we have z's, and it is a test now, and it's for the difference, p1 minus p2. Make sure you state this, not two prop z test. That's not enough. We want to state this. All right, we need to have our two independent random samples. Don't forget to put the word samples. All right, make sure that they are approximately normal sampling distributions for each one of them. So as long as each one of them is approximately normal, both of them together, the difference will also be approximately normal. So we have our four different conditions. Everything's going to be bigger than or equal to 10. And then for our independence one, each one of our sample sizes must be less than 10% of the population. All right, on our calculator, it is a two prop z test. If you want to write it out by hand, it's a lot of work. But the z would be the difference of the proportions minus 0, because the null hypothesis is 0, over the standard error, and that gets us our z, and then we use normal CDF to try and find the p-value from that. All right, or we just put it in the two prop z test in our calculator. All right, and then if p is low, reject the hoe. If p is greater than alpha, we fail to reject the hoe, and we write some sentences about the alternative hypothesis in context. It could be long because we're talking about two proportions and we need context for both of them, but I mean, you can do an extra sentence or an extra few words if it means getting a 5 on the AP exam versus getting a 2 on the AP exam. All right, so here is our first example. Researchers design a study to compare the proportion of children who come to school without eating breakfast in low-income elementary schools. A random sample of 80 students from School 1 found that 19 missed breakfast today. At School 2, a random sample of 150 students included 26 who missed breakfast today. Do these data give convincing evidence of a difference in the population proportion at the alpha equals 0.05 significance level? So we're comparing the proportion of students that had that missed breakfast at these two different schools. All right, so I'm going to draw my little cross. All right, in my first one, so we got school 1, so I'll label that p sub 1. And this would be the true proportion of students without breakfast. I guess you could say today or not, or whatever. P2 would be the true, at school 1, that's the important one. At school, I left out a C there. School 1. And then P2 would be the true proportion of students without breakfast. I know, it's like writing the exact same thing twice. Why can't I just put ditto marks? Write it. At school 2. There we go. A null hypothesis will be that they are equal. P1 equals P2. Our alternative hypothesis is we are just looking if they're a difference. So P1 does not equal P2, which means this is technically a two-tailed test. Our alpha value is 0.05. Our P1 hat, let's see, we had 19 missed breakfasts out of 80. 19 out of 80. So this would be our N1 down there. Our P2 hat is 26 out of 150. So that would be our N2 down there. Barely fit it all in there. Next up, so we want to state what test are we checking conditions for. So this is 2 samples. All right, we are working with Z because we're working with P, so it's a 2 sample Z, and we're doing a hypothesis test because we're given a significance level. So test for, and we can just say P1 minus P2. I think you can also say P1 equals P2, and that would be okay, but just stick with P1 minus P2. All right, we have 2 independent random samples. So whenever we have the 2 of them, we got to put 2 independent in front of it. That checks out. They're from different schools. They're both random samples. All right, so we have no overlap in our students. We should be fine there. All right, all of our normal conditions. So the first one, we got 80 times 19 out of 80 is 19, which is greater than or equal to 10. 80 times 1 minus 19 out of 80 is what? 80 minus 19 is what? 61, which is also greater than or equal to 10. That checks out. The other one, we've got 150, and 26 out of 150 is 26, greater than or equal to 10. Yep. The other one is 150 times 1 minus that, which is 150 minus 26 is 124, also greater than or equal to 10. So we've got our approximately normal sampling distribution. That checks out. And finally, independence. As an independent from any other samples, we've got N1 equals 80, N2 equals 150, which hopefully are less than 10% of students at each school. So as long as we have more than 1,500 students at the other school and 800 at the one school, the first school, we should be okay. All right, or sampling without replacement, which we are also doing, but that's fine. We're just going to write that. All right, and we're going to do a 2-prop Z test. We're back to doing a test now, not a confidence interval, although we could do this with a confidence interval just as easily if we wanted to. All right, so come on, come back. There we go. Stats, test, 2-prop Z test. There we go, much higher up, number 6. All right, and let's see, we've got 19 out of 80. And the other one, we've got 26 out of 150. Make sure we're putting them in the right order. All right, we want to see if they are not equal to each other. And we want to calculate. And make sure we write down our Z and our P for sure. So 1.168 is our Z. And our P value. Notice I write the word value here, guys. I've seen some of you haven't been writing it. Just write it. It helps you keep it straight from P. 0.24. All right, now there was another thing on that menu. We'll get back to that in a minute. But let's first come up with our conclusion. So there's our p-value. There's our alpha. So we're going to say since our p-value, which equals 0.24, is greater than 0.05, which was our alpha. So p is not low, so we fail to reject the HO. We fail to reject the HO, that they are equal to each other. That means we do not have significant evidence that the true proportion of students who eat breakfast, or actually who miss breakfast, I guess is what we're talking about, who miss breakfast, or you could say don't eat breakfast, is different. So we don't have evidence that it is different. Different between school 1 and school 2. All right, so if like we were doing an actual study, we'd have the names of the schools or whatever. All right, so that's how we do our hypothesis test. What is the p-hat value your calculator gives you? Pooled data. So what is that? So there's another thing on here. It is the bottom p-hat. So they gave us p-hat 1, which was the 19 out of 80. They gave us p-hat 2, which is the 26 out of 150. Those are these two things. This last one is what we called pooled data. So if we put it all together, that's what we get. And sometimes it's best to use pooled data. So like the p-hat value they give you would be if we were pretending this was one distribution. And we'd have 19 and 26 total that did not have breakfast. And then 80 and 150 total that were sampled. And that would be our p-hat pooled value. So that's if we put it all together. So just keep aware that sometimes we have pooled data and sometimes we don't. It doesn't change how we do our test, but just sometimes keep aware of that. If they ask you about it, that's what that p-hat is. All right, next one here. I think this is the last example for this one. Yep. So high levels of cholesterol in the blood are associated with a higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol with no history of other serious medical problems to investigate the question. So we get this no history of other problems to eliminate confounding variables. That's what's happening there. The volunteer subjects were assigned at random to one of two treatments. 2,501 men took the drug gemfibrozil, whatever that is, to reduce the cholesterol levels, and the control group, the other of them, the 2,030 men, took a placebo. During the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks, because that's what we were looking for. Do the results of this study give convincing evidence at the alpha equals 0.01 significance level that gemfibrozil is effective in preventing heart attacks? So it's asking us to do a test, a significance test, and we're talking about two different samples, and they have proportions of men in each sample that have had heart attacks. So that's what we are looking at, is the difference in the proportion of men that had heart attacks for those two different groups. All right, so P sub, I guess we can go 1 is the true proportion of men with heart attacks on gemfibrozil. Hopefully I won't have to write that much again. And proportion 2 will be the true proportion of men with heart attacks on the placebo. All right, so there I've defined both my P's. My null hypothesis is that they are going to be equal, that there will be no difference between the two. My alternative hypothesis is the results give convincing evidence that gemfibrozil is effective in preventing heart attacks. So if it's preventing them, the proportion of people with heart attacks with the gemfibrozil should be less than on the placebo. So that's what our alternative hypothesis is. All right, let's see. What else do we have? We've got alpha equals 0.01. We've got P1 hat. The proportion that had heart attacks on gemfibrozil was 56 out of 2,501. And the proportion that had heart attacks on the placebo were 84 out of 2,030. All right, so that's everything. So this is our N1. This is N2 right down there. So the name of our test is a 2-sample z-test for, and we can say P1 equals P2 or P1 minus P2. Either one's fine. All right, and we have 2 independent random samples. All right, so it said they were randomly assigned to treatment groups. So, and there's no one in both groups, so they are independent of each other. All the N times P conditions, oh boy. So we got 2501 times 56 out of 2501 gives us 56, which is greater than or equal to 10. We've got 2501 times 1 minus 56 out of 2501, which is also going to be greater than or equal to 10. I haven't worked out the number, but it's going to be in the thousands. It's 2,445, I think. So let me check my math. All right, the next one, we've got 2030, 84 out of 2030, which is equal to 84, which is definitely greater than or equal to 10. Forgot you always put in the check marks here. And then 2030 times 1 minus that, which is over 1,000. 1,000. Math in my head. So 50, 46. So 1946, I think. Somebody else check my math. And so everything's greater than 10. So we do have our approximately normal sampling distribution. That checks out. And for independence, all right, so we've got N1 is 2501, N2 is 2030, which is surely less than 10% of all. And there, I believe we were taking from middle-aged men with high cholesterol. But all right. That checks out. We've got millions and millions of middle-aged men with high cholesterol probably to choose from. All right, and then we've got a two proportion Z test that we're going to do on our calculator. So we just got to put in the numbers here, and it's been so long our calculator has already turned off on us and given up on us and moved on with its life. All right, so 2 prop Z test, there it is. And we've got 56 out of 2501. And then we've got 84 out of 2030. And we want to know, is P1 less than P2? So we want less than P2 and calculate. All right. And we say negative 3.67 for our Z. And our p-value, and be careful here. Remember, p is always a probability. It's a decimal. So 1 point something doesn't make sense. But then you look at the end of it, and you see this e negative 4. That means times 10 to the negative 4th. It means this number is so small, it's in scientific notation. So it's 1 point times 10 to the negative 4th. In other words, if we take this number and move this decimal up 1, 2, 3, 4 spots to there, that's what the actual number is. So we've got 3 zeros and then a 1. So our p-value is very small. All right, so since our p-value is low, since the p-value equals, and you can write it either way you want, 0.000191198 is less than 0.01. Right? Even our significance level is low, but this is much less than that because that's got a 0 there, that's got a 1. And that's our alpha. So p is low. We reject the hoe that P1 equals P2. So they're not equal. We're going with the alternative. That's our boy right there. We have significant evidence that the true proportion of people who take gemfibrozil, Gemfibrozil, will have, future tense here, will have fewer heart attacks than those on placebo. There we go. All right, interpret the p-value you got from part A and context for this experiment. All right, so remember the p-value means if the null hypothesis is true, this is the chance that we got the answer that we got. So if P1 equals P2, then the probability of getting the data or the results we got is 0.0001198. All right, so it's not very likely that the P1 equals P2. right, in this experiment because the probability here is so low. Right? If this number was big, then that's why we don't reject anymore. But when this number is small, that means the probability of that happening is really small. That means it's this if thing, this part is probably untrue. And that's how hypothesis tests work. All right, sorry if that's long, but these questions do take a long time to write out and to do. But that's it for 9.1. So check on the Google Classroom for some homework there.